Okay, folks, so here we have an HL extension for our Coulomb's law unit, so for topic 1.3. By the end of this, and in this video, we're going to talk about electricity and circular motion. By the end of this video, you'll be able to use Coulomb's law to solve circular motion problems. So let's go ahead and get started. So we're going to go ahead and start by reviewing circular motion. And specifically, what I would like to review is the equation for centripetal force. So remember, centripetal force is any force that keeps an object moving in a circular path. So we talked about the centripetal force of gravity and how that keeps the Earth moving around the sun. Now we're going to talk about how electricity can also be a centripetal force. So let's go ahead and review the pieces of our centripetal force equation. So first of all, we've got mass. So we know that our centripetal force is equal to mv squared over r. We know that v is our velocity, and actually it's really our speed, more accurately, because our direction doesn't matter here. And then finally, r is going to be the radius of our path, so radius of motion. Now, one thing that I'd like to mention is that we know that F equals ma. So our centripetal force is equal to m times v squared over r, meaning that our centripetal acceleration, is v squared over r. And that's going to be how quickly our object is moving. It's accelerating towards the center of its circular path. So when is the electrostatic force a centripetal force? We know that our gravitational force is a centripetal force when we talk about planetary motion, but what about the electrostatic force? Well, let's go ahead and talk about the Bohr model of the atom. So this is something that should be reviewed. So in the Bohr model of an atom, we have our positively charged nucleus, which is made up of our protons and our neutrons, which I'm just going to put a 0 because they are neutrally charged. So we can have however many protons and neutrons there are in that atom's nucleus. And around the nucleus, we have our electron traveling in a, we're going to say, circular path. Now, heads up, it's not always going to be circular, depending on which orbital we're in. We're going to be talking about, for those of you that remember in chemistry, our basic s orbitals, which are spherical. So our electron is going to orbit in a circular path. Now, just so that you know, this is a simplification of what an atom actually looks like. And later on, we are going to talk about, when we go into topic 7, we will actually talk about what happens inside of an atom. But for now, we're going to say we've got an electron orbiting a positively charged nucleus on a circular path. So, in this situation, the force that is keeping our electron on this path is our centripetal force, and it is going to be the electrostatic force between the proton, well, not the proton, the positively charged nucleus and the electron. So let's go ahead and work through an example. A hydrogen atom consists of a single electron orbiting a single proton at a radius of 5.3 times 10 to the negative 11th meters. Both the electron and the proton have a charge of 1.6 times 10 to the negative 19th coulombs, and the electron has a mass of 9.1 times 10 to the negative 31st kilograms. What is the maximum speed of the electron? So let's list out. So actually, what I'm going to do, I'm going to go ahead and draw a picture. We have our proton. We have our electron orbiting on its circular path. And here we have our centripetal force, which is also the electrostatic force between our proton and our electron. So I'm going to go ahead and erase my picture because it's a little big. And what we'll do is we will go ahead and list out our givens. So from this question, or from the problem, I know that I have a single electron and a single proton. So I'm going to go with Q1 and Q2. And in fact, I'll call them QE and QP. And our electron is going to have a charge of negative 1.6 times 10 to the negative 19th coulomb. I'm going to go ahead and ignore that negative sign for now, though. So I'm going to say 1.6 times 10 to the negative 19th coulombs. I'm going to say the charge on the proton is the same. And the reason I'm going to ignore that sign is it really only matters when we're talking about the direction of motion, which we will get to at the very end of this problem. So again, we've got our charges. We know that the distance between our charges is 5.3 times 10 to the negative 11th meters. And we know that the mass of the electron is 9.1, I'm going to call that ME, 9.1 times 10 to the negative 31st kilograms. That's all I know, and I am trying to figure out my unknown, which is going to be the maximum speed of the electron, v, or VE if we wanted to. I'm just going to leave that as V. So let's move forward to the trickiest step of our whole problem, which is, of course, figuring out a useful equation. So let's start with the equation for centripetal force, since we were trying to figure out the speed of the electron. So we know that the centripetal force is equal to mv squared over r, where m is the mass of the electron, v is what we're trying to find, its speed, and r is the radius. So we know the mass of the electron and we know that distance, but we don't know what the centripetal force is, except we know that our centripetal force is equal to our electrostatic force. So let's go ahead and on the left side of my equation, I'm going to replace the centripetal force with the equation for the electrostatic force. So I know that the electrostatic force is equal to K times the charge on the electron times the charge on the proton divided by the distance between them squared, which is equal to the mass of the electron times its speed squared divided by r. So what I'm going to do next is I'm going to get my v by itself by multiplying both sides of my equation by r over the mass of the electron. So I'm going to have those two radiuses cancel, and I'll have just one distance, one radius, in the denominator of my fraction. And what I'll get is that k times the charge on the electron times the charge on the proton divided by the mass of the electron times the distance between the electron and the proton is equal to v squared. And if I take the square root of both sides, so I'll take the square root here, I'll take the square root here, what I get is that v is equal to k times the charge on the electron times the charge on the proton divided by the mass of the electron times r, and the square root of that whole big ugly thing. Ugly equation, but not too hard to find, right? You guys can do this. So let's sub and solve. We've done the hard part. Now we're just going to plug in the rest of our numbers. So v is equal to the square root of kqqq, so 9 times 10 to the 9th, times 1.6 times 10 to the negative 19th, times another 1.6 times 10 to the negative 19th, divided by the mass of the electron, so 9.1 times 10 to the negative 31st, times the distance between the electron and proton, which is going to be 5.3 times 10 to the negative 11th. Sticking that all in a calculator, I get v is equal to 2.2 times 10 to the 6th meters per second. So there you have it, folks. You can now solve electrostatics problems. And as I promised, we'll talk about direction now. And all I'm going to say is we don't care about the direction because we are finding speed, which is a scalar quantity. However, the direction of the force, of our electrical force, is going to be the same as the direction of any centripetal force. That is to say, it will always be towards the center of the circle or towards the proton. So let's talk takeaways. First of all, we reviewed that centripetal forces keep objects moving in circular paths, and we talked about how in atoms, the electrostatic force acts as a centripetal force. So we can use our centripetal force equations to solve electrostatic problems. So now it's your turn. Go forth and conquer. Happy solving!